So hi everyone. I don't know about you guys, but sometimes you sort of wake up and you read the blogs and there's all these fields and data science is amazing. But you do sometimes wonder, like, what's the whole crowd doing and what is it that we're actually doing? And it turns out that there's these three schools of doing things. At least that's when I look at things, it seems to be the obvious case. There's this triangle. On one end, you have these people that call themselves frequentists, or that people call frequentists. There's this other area that are filled with people that call themselves Bayesians. And then you have this other area where people call themselves machine learning specialists. And even though we're doing similar things, we're trying to do things with data, it seems like there's different things happening. And even though it seems that it's very clear that if you're from here, you should be doing this, it seems to be a bit less clear that if you're here, you should consider this. So that's sort of the topic of my talk. I'm going to try to convince you guys that if you're thinking a little bit more along the lines of this school of data, you can solve problems in a different and sometimes better way. So there's a whole lot of stuff I'm going to talk about. So let's just go ahead and talk about what the textbook Bayes rule actually is. In essence, the fact that there's this thing called probability theory means that if we just adhere to the rules of math, we didn't have to do any thinking ourselves. And Bayes' rule is just a summarization of that. Very simple example. I think I can assume that everyone has seen this formula at least once or twice, so I'll not go over too much in depth of it, but I will give a...
Valid prime.
It is valid. Okay, good. N is 1. Good. But let's assume that I have this situation where I'm rolling dice, right? So here I'm rolling 1 die, here I'm rolling 2 dice, here I'm rolling 7. And I'm showing what the likelihood is of the number of eyes that I am rolling. The cool thing about Bayes' rule is that I can then say, given that this is the number of dice that I've rolled, then this is the number of eyes that I'm seeing. However, the trick is, if I then start to think about, hey, given that I see this many eyes, well, how likely is it that I roll a certain dice? Instead of looking at it from this way, I can look at it from this way. And that's a very convenient trick. So let's go over a very textbook example and show some more cool things you can do with this very, very simple rule. So let's assume that there's an epidemic. There's a very scary disease, and we're worried about that. A person has a probability of 1 over 100 to actually have the disease, which is very high. Henceforth, the authorities decide to test the population. Like any test, the test is not generally reliable, and 1 out of 110 people get a positive result. But given that you have the disease, the probability of getting a positive result is 65 over 100. So this should feel like your first year's college course in probability theory, and you can fill in the numbers, and you get this probability out. This so far shouldn't surprise anyone. So far so good. We have applied Bayes' rule, we've learned some stuff. This is kind of neat. We can infer more things though, and that's where the magic happens. So I'm assuming I've not lost anyone here. Suppose that we can calculate all of this. So we can calculate the probability that you have the disease given that you took a certain test. And it's because we know all of these things. We know the likelihood of getting a positive result in the test, likelihood of getting the disease, and the likelihood of getting a positive test given that you had a disease. It also means that we can infer the fact that the test came out positive if you didn't have the disease. That's because we can split up the distribution appropriately as well. And if we fill in all the numbers after some calculation, we get the number out. So far so good, but this is sort of arbitrary. Why is this interesting? Well, you can do this for getting 2 positive tests, and you can do this for getting 3 positive tests. And again, you can argue, this is interesting, Vincent, but what's the point here? This is just arithmetic so far. Well, the trick is, the situation where I take 1 test and I have to determine if you have the disease, I can now start to think about what it might be like if you took 2 tests. Using all the inference we've just done, even though initially I only knew about, you tick that you have the disease, what's the likelihood of getting a positive test, I can use that knowledge to infer what the likelihoods will be if you have 2 positive tests. I can do the same thing if I take 3 tests. All the math is just there, and I just have to follow probability theory. And what might not seem as a very powerful thing at the moment, you will hopefully agree this is somewhat logical. A powerful thing is that suppose that this is prediction time. I have a model, and I have to predict something. I now have a model that can accept different input at prediction time. Most random forests don't work in a way that if I have more data available to me, that then the prediction becomes better. I have to retrain the whole thing. So with this Bayesian mindset, we seem to be able to do some things that in the machine learning land appear like it's sort of voodoo. So this is sort of cool. Via Bayes' rule, we can infer information about situations that we didn't initially think about. And the trick here is that we clearly define the uncertainty that we have, and that we can infer the rest by just applying probability theory. In this specific case, the main cheat was that we can realize that the tests are independent of each other, given that you have a certain disease. But the cool trick here is that we can use the same model to have different output at prediction time and still adequately be able to manage everything. So this is a textbook example, and there's a post on my blog with all the numbers if you want to calculate it. But notice that we have this nice graph here, and we can sort of think about what that graph might mean. Let's do that. Let's talk about probabilistic graphical models. So we had a graph here, which talks about the structure of our system, if you will. Given this, all of these things are independent of one another. So what do those graphs in general look like? And I'm going to use a very cool library called pomegrenate. It's fairly new, and it does some amazing magic for what I'm about to do. Let's assume a certain situation. I'm not arguing that this is a very realistic situation, but let's say that there are 3 broadcasters at a local news station. And they're all going to be predicting the weather. These are weather forecasters. Let's assume that Alice is great. She's super accurate. And let's assume that Bob is terrible. And let's assume that Claire is all right. Let's then also assume that, if I know the person, I know about how likely it is the weather is going to be predicted correctly. But let's then also assume that depending on the weekday, we might know a little bit more about whether Alice is going to be predicting, or whether or not Bob is going to be predicting, or whether or not Claire is going to be predicting. And you should notice that this sums up to 1. And obviously, this then also sums up to 1. And let's then also assume that given a day of the week, it might be a little bit more sunny. This, oddly enough, is not that insane. Turns out there's places in the world where on the weekends, because there's less cars about, there's actually less pollution, and henceforth there's more sun. This is the least ridiculous assumption in the entire model. Anyway, if I were to then construct the logical graph that comes out, and I'm only thinking about, given this, is the rest then independent? This is what it should look like. It's a very simple, albeit strange, probabilistic graph. Not strange because of the structure, but strange because of the example that I've picked. Now, you can construct this in a library called pomegrenate, and this is sort of the pseudocode of how you would do it. You would start at the beginning of the tree. So given this, we should be able to construct that. So the first thing you would have to construct in this tree is the term D, which is the day of the week. And you have this discrete distribution available to you, which you can just use. And there's also this conditional probability table. So the idea would be, given that it's a weekday, the probability of, if you have Alice, it was very likely that it was on a weekday. And you can fill these conditional probability tables in with the idea, given this, I can do something about that. And then given this, I can say something about that. And you can construct the entire tree. You combine them all together. Once you've defined all the states, you say how the states are connected. And you have this thing called a network, which you can, at the end, tell it to bake itself. This is syntactical detail, but it's a fairly clean API. So definitely check this library out later. The cool thing then is I can ask the system then, suppose I know who did the predicting, what's the probability of the rest? And just like in the example we saw before, the amazing thing now becomes, this is a system. If I put input in here, the rest is inferred. And this is where something freaky happens. Not only do I now have a system where if I only know P, I can infer the rest, but I also get the system where as more data becomes available to me, the other variables will become more accurately predicted, that is. And that is a very interesting system. Very few neural networks do this. But let's see what the outcome of it all is. If I say it's Alice, it turns out it's probably a weekday. We're very sure about who did the predicting, because that's the input of the model. We're also pretty sure it's probably sunny, and this is due to the fact that it's probably inferred for the day of the week. And we also know something about whether or not it's going to be predicted correctly, and that's, of course, because this is what we put into the system itself. It's the exact same number we put in the conditional probability table. We can do the same thing for Bob. the probability that it will be predicted correctly is, of course, quite a bit lower. And here's a situation where I put two things in. And obviously, in this small example, these will be the exact probabilities that I put into the system, but that's kind of the response that I expect. So if the weather's predicted correctly, it's able to infer that it was most likely Alice, but it could have also been Bob, and it could have also been Claire. But the main interesting thing here is, hey, at prediction time, given different data sets, this kind of system is able to deal with it. So these types of models are very powerful and flexible, and one of its most powerful features is that it can logically handle missing data at prediction time. So suppose, for example, you might be an airline, and you're not exactly sure if this airplane is going to come in on time or not, but there's these few things that you know, and as time moves on, more information is known to you. This might be a model that's very useful, because you have one single system that you can ask many different queries. And again, the example I've given here just handles discrete models, but mathematically, the relationships that we've just defined can be continuous as well. Coding these things up is usually the harder part. Pomegrenate currently only offers discrete distributions, not continuous ones. There are sampling libraries that offer a form of alternative, but I am sort of more hoping that we can get this pomegrenate library to work with continuous distributions as well. Shout out to the guy that made it. I will also do a unconference session with this library, so if you're interested in, hey, how does it work, can we code it with a bit, 5 o'clock, that room, I will do a small demo and explain it to you. Would also love it if you guys maybe considered contributing to this package, because I think it's going to be the next great thing in probabilistic programming. So these were examples where we had a certain type of model where, hey, this sort of comes from the Bayesian world. This type of modeling is nice. But it's also the Bayesian thinking that sometimes really shines. I'm going to share an example with you from a book from David McKay, who unfortunately passed away this week. But I'm going to translate an example from this book to hopefully an example that you guys can imagine. So let's assume I'm Dutch, so I'm from Amsterdam. And in Holland, I'm not sure if you have them in England as well, we have these very small backyards with these small walls. And suppose that you're like a true crazy data scientist, that you're always collecting data. You can imagine at some point, if there's a very tall person, you actually see the tall person pass by. And let's assume that you're also deaf, so you can only see the people. But you are aware of the fact that only tall people pass above the wall, and henceforth, what you see, the average length of people, is biased. But you know how the data is biased. But you know that there's bias in the data, but you know that there is bias because you're only measuring people above a certain height. The question I would like to pose then is, what can we then say about the entire population? So we know that we've got biased data. Can we say something in general about the rest of the people? And if you're, say, a pure frequentist, this might be tricky. Whereas if you're a Bayesian, this is actually quite a lot easier. Now, I will give the example differently because height is a bit of a nasty example because we kind of have to assume that people are distributed normally. So you probably have like an average and some variation. So let's think of a different example. But this is sort of the kind of problem we're trying to tackle with this way of thinking. So let's pick another very realistic example. Suppose that I have a call center. And suppose that we're interested in knowing how long people wait in line. And let's suppose, and this is a big assumption, but it's mainly meant to push the example forward. Suppose that we only measure people in the waiting line who've been waiting for a very long time. Let's say after 7.5 minutes, then they start to complain to the other customer service, and that's when we start to measure them. Anyone who's been waiting less than 7.5 minutes, we don't measure simply. So what can I then say about the waiting time in general? I only measure a few people, and their waiting times are biased. Let's say that they're larger than some value m, and I know nothing else. Again, I'm hoping that you're aware of what the problem is, and that you may realize that this indeed feels a bit tricky. Okay, let's first then think about how we're going to simulate the waiting time. Usually one uses an exponential model. Basically, it means that we have this variable called lambda. That's the hyperparameter of this distribution. And the idea is there's a lot of people who wait for a very short amount of time, and there's some people who wait for a very long amount of time. But this is usually a very thin tails, and most of the density of the distribution is around that corner. But for two different values of lambda, this is a higher value because it has a thicker tail. This is what the distribution sort of looks like. And we're interested in finding out what lambda is the appropriate one, given that we have biased data. So gee, how do we do that? Tricky, tricky. There's lots of sampling techniques. I guess I could go ahead and try, but I kind of wanted a pure solution. Bayes to the rescue. Suppose that we've biased data, then this is basically the metric we're interested in. And let's, do the math. A given B, and then you just fill in the formula. It looks like this. Sure, it's a continuous distribution at times, but this is what it looks like. So given a certain value of lambda, we should be able to say something about the likelihood of how the data got created. But, well, now that I think about it, we can make it a little bit simpler, because let's assume that I'm just optimizing this. I'm only interested in finding the max value for this. And I'm not as much interested in what this probability is, because it's just a normalizer. I'm more interested in what the maximum argument for this would be. So I can drop the PD bias. And to make it even simpler, if I want to know the likelihood of this bit, and I have a data set, then basically I can use the law of probability. I'm assuming that there's some form of independence between these numbers here. Then I can say just multiply every single data point, and then you have a combined likelihood. And of course, all of this just follows from using this Bayes rule trick, which isn't really a trick, it's just the law of probability. OK, so this seems like a genuine OK way to go, but we want this to work. So let's code it up with a couple of for loops. First, it's all right to mention that this, of course, is the distribution we might be interested in, giving a certain lambda. But we have to accommodate for the fact that we have a certain m. So we only measure above a certain threshold here. Let's say this one. So then this likelihood should be the likelihood of this beautifully painted red bit. That's the distribution we're actually interested in, because we're interested in when the data itself is biased. So this is the distribution we're actually pulling from. It's a distribution of interest. And this is the only hard bit, because the rest, you can normalize the distribution. So suppose we have this bit. This bit has to integrate all out to 1, so we have to normalize that. That's what I do here with a bit of math. But I guess instead of focusing on the math, the easiest way to do it is just to write a couple of functions and for loops. So let's assume that given a certain lambda and given a certain value of m, I just have this small function that can calculate the probability that x came from this distribution. And let's also do the same thing for, instead of having x is given lambda, let's also have one for a single x. Again, let's not focus on the code too much, because I can also just plot it. Given different lambda values and given the same m value, this is what different distributions might look like. And given the same lambda value but different m values, this is what the other distributions look like. And the idea is, if I measure a certain point of data, let's say this one, I had a data point at 10, now this is a likelihood, and that's a likelihood, and that's a likelihood. Similarly here. If I had a data point coming in here, that would be a value for a likelihood, that would be a value, and that would be a value. And I have a way now to, given a certain m, compare different likelihoods from lambdas to actual likelihoods that I can multiply. So I can combine it all, and given some data, let's say I measure these numbers, and I have a certain m, and I'm going over different lambdas, and I can have different distributions appear. Well, this is kind of hypothetical, so instead it might be best to simulate our own data and confirm that it actually works. I think that this might be more appropriate. So let's say the true lambda is equal to 1. I have this m that's equal to 6. I'm generating a whole bunch of random exponential data, and then I only make a subset of it, and I only want to have the values that are actually larger than m. I'm going to do this a bunch of times to show that this algorithm actually works. So let's say I have a large subset, a very large sample. I take a subset, and I only have 2 values. And remember, the true value of lambda was equal to 1. Then what my distribution says is, well, if 1 is over here, it's not completely maxed out over there. It thinks that the true lambda might be a bit smaller. But instead of giving like one single estimate of the maximum likelihood, I now have a distribution of what potential values of lambda might be. So instead of focusing on a single maximum likelihood estimator, my estimation becomes more of a likelihood instead. And that's usually what Bayesians do. Instead of saying, hey, I'm uncertain about my data, but I'm certain about my model, Bayesians prefer to say, well, I'm a little bit uncertain about my model, actually. I'm actually quite certain about the data. So this is if I have 2 points. If I then get more points, you will notice that it will actually start to converge. And if I get even more points, you will notice it actually gets there quite easily. So what happened here, just as a basic summary? We started out with a problem that was kind of tricky. And yes, we had to do a little bit of math. But the only math we really had to do was to acknowledge that we had a Bayes rule here and that we had different distributions here, which needed some probability theory. But it did allow us to get this very nice model out, where if I get more data in, I'm able to update accordingly. So it's kind of fitting for more of a real-time purpose. So these are all data science topics, and that's fine. But I even found that Bayes' rule can help in different fields like optimization science. So let's pick a optimization problem that we know the answer of beforehand, and let's see if probabilistic thinking like Bayesians do can even help us here. So let's pick a very silly example. Suppose I have a 1x1 square, and I'm interested in finding the largest triangle. This is very easy if you're a human, because you just know top, middle, and left, and you can make a triangle appear that's huge. But if you tell this to an OR algorithm, it needs to figure some stuff out. So here's what I'm doing. I'm just going to create random points in the 1x1 square. And I'm going to look at the area of the triangle that's there. That's what this shoelace function does, by the way. And this is the distribution of area, given that I have random points. And one thing that you should notice, if we just take the random approach, we're actually sampling from the area we're least interested in. We want to sample here, because this is where large triangles are. But if we just sample randomly, we get the small triangles out. A little bit of math. One way of looking at it is to say, OK, I now have a probability density distribution of the area. That's sort of the histogram you've just seen. That's fine. Instead, how about with probabilistic thinking, we turn it on its head? So instead of saying we're interested in the probability of the area, let's say we are only interested in points where the area was above a certain value. And once we've selected that subset, I'm interested in the distribution of x, and x being the location of the points. And to be very specific and exact, let's say that x is a vector of 6 variables, x1, x2, x3, y1, y2, y3. So I've sampled all of this randomly. I then have the histogram. I cut away the areas that are small. And then I look at what the next distribution might look like for the x's. And there's this very lovely library called Corner, where you can just have a high-dimensional space and have it plot it out for you. That's what you see here. So this is for x1, x2, x3, y1, y2, y3. And you'll already notice that I'm only doing a little bit of inference, but it is noticing how to do this correctly. If I want to have large triangles, it will be appropriate that the x1 and x2 values are far away from each other, because then the triangles ought to be a bit larger. I think I can zoom in on that. Yep. So large triangles will be far apart, which is sort of what you see here. If x1 is small, x2 ought to be big, and vice versa. And that's interesting, because if I look at x and y combinations, then you notice it's fine if x and y are in one corner, or if x is small or y is big, or they're both big, but they're not going to be anywhere in the middle. And that's also a property of a large triangle. And the trick here was to think, again, a little bit probabilistically about it. What am I interested in? Well, I'm not really interested in the area. I'm more interested in the distribution that generates triangles with a high area. So let's turn this into a learning step then. So if I have this histogram, how about I take the top half, learn from that, get a new distribution to sample from. I think I used the kernel density estimator from scikit-learn to do this. This was the original one. And let's do learning from it and then sampling new points, and then looking at what the new area will be. And suddenly, we're sampling areas that are significantly larger. And we can repeat and do it again. So again, we would say, you get the biggest half, sample from it again, get the biggest half, sample from it again. And I think I did this 3 times, and then I had the biggest triangle. So the idea is to repeat this idea until we have some form of convergence. Note that m in this case can be chosen automatically, such that m is equal to the average of the areas. And the cool bonus with these algorithms is that we can use inference on our simulated data to learn more about the nature of our optimization problem. And you should notice some form of similarity here with genetic algorithms. Basically, genetic algorithms do one thing well, and that is do a biased search. That's what Bayes' rule can help us do here as well. So it's kind of nice that we can get Bayes' rule in here to even solve problems that typically are not part of data science. In this next bit, I will talk about how Bayes' rule inspired me for some feature engineering. But I do want to double check if everyone knows what I'm talking about. Does everyone know this game? Yeah. Yes? Like one vain guy in the back, yes. It's not even like a full-blown yes, I play this game, but sort of yes, I hate myself that I play this game. I've spent too many hours playing this game as well, but I was just doing it for the data science of it. So there's this great franchise, it's called Blizzard, and they make great games. I mean, the World of Warcraft was from them, and they have StarCraft, which is basically the same, but more pew-pew. And the idea is that there are two teams, and you get to pick characters, and then the question is which team will win. And something that seemed interesting to me, at least, was to think about, hey, suppose that this team selects that character, this character, and that one, and the other one selects this one, this one, this one, and this one. So you probably have Team Space Warrior versus Team Swordsman or something. But can we do some inference and see who might win? And if you think about it, it's actually kind of hard. So I have some data. If you go on Reddit and type in Heroes of the Storm match outcomes, you will find a guy the guy has this service called Hogs Logs or something, where you can send your own video game data, and it tries to give you some information on how you can improve your game. In the meantime, it collects all of these game outcomes, and it tries to make this internal ranking to help predict players who might win. But it also means that I have about 500,000 games available to me, so I have some form of information about which character choices might be good. But if I look at the search space, so let's say n is the number of heroes in the game, if I only have 20 heroes, and I think at the moment we have 40, if I only have 20 heroes, and even if I have 500,000 games, then there are more allocations possible of heroes than I actually have games in my data set. So any random forest will have a bit of sparsity issue here. And also, if I think about the data structure, this doesn't really fit well in a standard table. So you have team 1 heroes, which would be 40 columns, and then a couple of them will have ones, and the rest will be all zeros. And at the end, it should say team 1 or team 2. So already I'm having a bit of trouble getting this to work in scikit-learn. So I actually, when I will run this, I will expect a lot of machine learning to fail. And this is something, without running any code, I can already imagine happening. We have 72 columns, out of which every row will have only 10 items filled in. And I think, given the fact that we don't have billions and billions of rows, even random forests and deep neural nets will just not be able to get any pattern out of it. Will mostly be treated as noise. So instead of trying hard to create features that might perform well in this case, because we might be able to extract some manually, let's see if we can use a little bit of domain knowledge to help us out probabilistically instead. So this is team B, this is team A, and whatever I'm doing in the middle, we need to have some features that go to P. P is some form of prediction algorithm, and I want to generate some form of features here. Okay. Well, one thing I could do is I could say, this is the first hero from team A. That's the first hero from team B. Let's just do something with combining them in a node here. And let's do that for every single hero. And again, this should be sort of seen as some form of flowchart. Given this state, that state will be filled in. And yeah, if I draw all the lines, it becomes a little bit hazy. So let's instead introduce a new notation. People like to call this plate notation. The idea is for every I in team A and every J in team B, we have all these nodes in the middle, and they will all go to some form of prediction algorithm. Let's keep it in the middle what that prediction algorithm exactly is. What I can then do is, well, suppose, given this and given that, I could have some form of distribution here. Namely, given that team A picked Muradin and team B picked Kerrigan, I can sort of get this beta distribution out for what is the likelihood that team A might win. It's kind of like a B test in that sense. How likely does it that this team will win or that team will win, given that I only know this? And I do that for every single hero combination, if you will. And what you can then do, you can make this pretty GIF, where you generate all these distributions. You'll see about 25 of them. And then, when there is 25 of them, you'll see them combined in this new distribution. And again, this is what the feature engineering bit would do. And once you see the black line, that's what I would call my predictor. What it would do is it would take all of these distributions and use probability theory to combine them all back into one single distribution. And that distribution will tell me how likely it is, as a guess, that one team will win from the other team. And be reminded, if you're paying attention, you will notice, gee, all these values are actually sort of around 50%. So is this model performing badly? Yes and no. You have to imagine that there's a team of, I think, 40 people, half of which probably Korean, who are doing their best to optimize this game for balance. So if I'm able to find any imbalance whatsoever, that's already something I could potentially sell to Blizzard as a game improvement. If I'm able to get, say, 1% chance out of this, that's already millions of games. But while I'm at it, I mean, this is all right. But let's just think about properties here. Would this still work if, for example, I knew all the 5 players from this team and maybe only 3 players from this team? Well, sure, I'd be drawing less of these, but the whole combining trick would still work. And it's actually robust as well. I can have some form of prior, maybe, if I don't have any information about Team B, so that's kind of nice. But maybe we can even expand a bit further. So how about, instead of just taking one hero from Team A and one hero from Team B, how about we take 2 heroes from Team A and 2 heroes from Team B? We would have a lot more nodes in the middle, if you will, and each node would have less data. But by the fact that I would have a lot more nodes, I might be able to improve upon that. OK, so that's kind of nice. And even now, I have the characteristic that if I know, say, only 4 players from Team B, this whole model would still not break like a neural network would. And while I'm at it, how about we create these 2 models next to each other? There's some form of predictor that takes whatever comes out of here as input. And we then later combine these 2 together and build a huge ensemble out of it. Or maybe even at the end here have a neural network which takes all of this as input. Is this Bayesian convolution? No, it's just graphical modeling, but it has a lot of nice properties. So I actually went over this quite fast, a little quicker than I anticipated, but I hope at least I have convinced you that some of this Bayesian thinking is something to be noted and something where you can actually play a lot with. But to convince you guys of how I at least experienced these 3 schools, let's do one more small example. Because whenever I talk about this sort of thing, you go to a client. The client has a classical textbook statistics background. And the first thing the client will go is, all this Bayesian stuff is nice, but I don't see any confidence intervals or p-values or statistical significance tests. And this feels all very different. How should I interpret this? Well, we kind of come back to this triangle then. And I think this is the best way to summarize it. All models are wrong. Some models are useful. What are you most uncertain about? Are you unsure about the data? And are you trying to fit the best single estimator to summarize this? This would be sort of maximum likelihood regression. And let's say you're doing a normal regression. You would probably then say, OK, I have the maximum likelihood estimator. I'm going to fit some sort of t-distribution on it. And I'll see if it deviates from 0 by doing a t-test. You can also say, well, I'm unsure about my model, and I accept my data to be the only ground truth. In that sense, the data is the truth. And you will then say, well, I'm not sure about my lambda, but it's probably in this region, and I have some probability distribution, which I think is the best way to describe the uncertainty that I have. What you can also do is you can say, I'm not uncertain at all, because I have awesome test set performance. That's what machine learners tend to do a little bit more of. And to give the most blunt example of it, because we're doing Python, I'm sure we like pandas, this is an image from matplotlib, and this is an image of a panda. And what I then did, I looked at all the pixel values. I believe then black would be close to 0 and white would be close to 1. And I figured, let's maybe see if different schools think differently about this. How can I infer what a panda is if looking at this? And what I can do is, if I'm a frequentist, we get something that's obviously a little bit weird. I can then say, what's my maximum likelihood estimator? Well, then it says the average panda is indeed gray. The thing that I find scary, though, is that if you then say, OK, let's look at the standard deviation and the variance and plot that over it, you see that this model allows for values that are smaller than 0 and larger than 1. To me, that seems rather unsensible. So what might, and again, this is sort of my blunt translation of how I think frequentists think. I'm sure there's sensible frequentists out there. This is what a Bayesian, I guess, would do more. As a Bayesian would say, I'm not going to summarize all of the pixels together. I'm just going to talk about the uncertainty that I have for each individual pixel. And then something which I find sensible comes out. It's not super likely that a panda is gray, but it's probably a little bit more black and white. This panda in particular is a little bit more white, which is the case. And machine learners, of course, would go, I don't know what a panda is, but my test sets suggest that I have this amazing performance. So in general, I always find that if I'm going to be anywhere, I'll probably be around this corner. This feels very comfortable to me, and also if I think about what's new and where most excitement is, I feel very comfortable being here. A deep neural network, what's the Bayesian interpretation of this? That's the stuff that I like working on. I tend to take these people a little bit less seriously, but in all honesty, I also sometimes use some things from that school. If I do regression for the first time, I kind of like the fact that I can interpret the t-statistics to say whether or not a certain type of column can be taken out or not. If you're going home with anything, please just remember, never let your school get in the way in your education, and more specifically, give this area of the triangle a chance. I mean, there's freaky stuff out there which might feel as voodoo, but stuff that's actually based on common sense because it's all just probability theory. Well, that's what I got. And before people start a rant, I'm making fun of this, obviously, but this is, of course, sensible, right? No, but in all honesty, I'm making a bit of a fool out of this, but it is in some way sensible that if you don't know exactly what you're doing, because it's a huge black box, but it performs well and keeps on performing well, always, then you might still have a sensible model. I'm not saying you should completely ignore this. However, with this example, the only thing I do hope to point out is that there are some preferable aspects to modeling things this way.
Questions? Sorry if this sounds like a blasphemy. From what I understand, which is, I mean, I didn't know much before, let's say.
Okay.
Well, one...
You can be blunt, right? I mean,
no, one good point of this picture is that it tells you more. So it's a bit... If I ask you one number, you lose part of the advantage. But the point is, why couldn't I talk about statistical significance from a plot from the result of Bayesian?
So immediately you have pointed out to some of the weakness of this point. I've purposely chosen this example such that I can say, hey, if you're taking the very, very classical thinking, it doesn't apply to this one example. That's not to say that it will fail for every single example. I'm just using this point here that in this case, I'm making fun of both the frequentists and the machine learners here to point out that Bayesians sometimes actually have a very nice way of thinking about things. That's not to say, usually for a lot of problems, if you were going to say yes or no in terms of significance, both of these two schools would overlap in their opinion. Okay. But there are these slight little differences, and this is the best one I could come up with as an example.
Hi. Thank you for the talk, first of all.
Thanks.
I have a question about, in the example that you showed about the waiting of the clients.
So the weather one.
Yeah.
Yeah.
People started to complain after 7.5 minutes.
All the way back. This one.
Yeah.
Yep.
So in your model, you went quickly on the assumption of conditional independence. Mm-hmm. And I'm guessing it's because numerically, when you do high dimensional integration, it becomes very intractable. So, because I've never used it in practice.
Oh, sure.
Do you always in practice when you go for a Bayesian approach, do you always go for conditional independence so that you can actually...
But the subject that you're touching is the exact weakness of this type of modeling. So this is very easy if I know the structure of the tree here, right? And this is the assumption, right? I know something about the conditional independence. What you could also do is you could say, I don't know the structure, let's try and learn that. You usually get into heuristic country when you do that, and there's no guarantee of optimality. So to get this to be very tractable, I am making these assumptions. And what I'm hoping is that as a sort of domain expert, that this tree that I've generated is sensible. But you are fair in stating that that's a bit of an assumption. It's certainly the case.
So in practice, people always make that assumption.
Yeah, but then again, any model does. Even random forests have some form of assumption, namely that you can make so many trees and that that's logical.
Thank you.
But again, all models are wrong. Some of them are useful. If you're interested in this, by the way, I'm going to give a small demo. I'd love to hear some feedback. Yep.
Okay, final question.
Could you recommend any resources for a non-mathematician to learn
Yeah, a bit of
learn this way of thinking? And,
sure, a bit of shameless
probabilistic graphical
shameless
models and
thing
so on.
then. I do have some advice. There is this amazing blog that I write. But now there's a tutorial on how I did the inference thing with a little bit of math, just a little bit of it. I found that it was trending on I think DataTow at some point, so I guess some people will like the stuff that I write about it. If not that, there's a couple of books which are a little bit mathy, but not too mathy. And those are the 3 books I recommend to any data scientist. There's Bayesian Learning and Machine Learning by Barber. There is Information Theory and Neural Networks. I think the book's called from David McKay. It's the reference I made earlier. And there's Machine Learning from Bishop. And the cool thing about those books is they all start with, this is probability theory, and this is Bayesian thinking. And only then do they talk about machine learning. And even then they try to stick some Bayesian thoughts into how they coincide. I think blogs and those couple of books would be your best bet. That's how I got started.
Thank you. We return at 3:30 for the final session. Please thank Vincent for his Bayes talk.
Thanks. Oh, wait. I want to do one joke. So the Bayesian goes to the frequentist and says, "Oh, you're very average." And the Bayesian says, "No, you're mean."